This is in a way part 2 of a talk that I gave about a year ago in my fight against surveillance capitalism. And in this part, I would like to show how we can use mathematics at least as part of our fight in this important movement. This work is not just done by myself. I have some brilliant collaborators. One is Roman Machinen from UC Irvine, whom I think you all know, so no further introduction needed. The other one is Maj Boedihajo from also UC Irvine now, a brilliant young mathematician from whom we will hear much more in the future, I'm sure. And I would like to acknowledge my sponsors, NSF and National Geospatial Intelligence Agency. So what am I talking about is surveillance capitalism? Well, let's start with the two main companies that have pushed this movement of surveillance capitalism. One is Google. You all use Google probably every day, unless, like me, you switch to DuckDuckGo meanwhile. If you use, for example, a cell phone that's run on Android, you should know that the reason that Google developed Android is that it can spy on you. It's not really to provide the service of a cell phone, but it needed to get access to your data beyond your Google search. And Android allows it to do that. And why do I say that? Why is this not just another conspiracy theory that I'm throwing out here? Well, if you turn off your cell phone, Google can still locate you. If you think, well, then I just take out the SIM card. Well, that Android is designed in a way, even if you take out the SIM card, Google can still locate you with the cell phone. So there's no way you can opt out. So it's really a means to spy on you. Now, the other conspirator here is Facebook, and the name change doesn't change the main strategy of Facebook to gain access to your data, to invade your privacy, and to sell the data to anyone who wants to have them. And for example, Facebook tried to make a deal with the banks in the US to get access to all your financial data. Well, the banks didn't really like the deal. So what is Facebook's next step? It's coming up with its own currency. This is just one example. Another example is when Europe released its new privacy laws in 2016. Facebook until then had all its non-US users enlisted under Irish law. You know, all the users that were not in the US, doesn't matter if it's South America, Africa, Europe, they were all run and registered under Irish law. After the new Europe's privacy law, Facebook said, well, you know, in spirit, we want to follow this law. It's very important. We don't have this law in the US, but in spirit, we want to follow it. Secretly, they moved all non-European users into US law. So secretly, they did something very differently than what they said officially. That's a strategy that Facebook is following all the time. Indeed, if you look at people working at Facebook, they're actively involved in AI. You would see that they also follow this philosophy. There's a guy who's not working at Facebook, Benedict Evans, who recently, or some time ago, tweeted, "You should own your data is such a meaningless bullshit slogan." Something I don't agree with, but Facebook's chief AI scientist, whom many of you probably know, happily retweeted this. So he follows that same sentiment. By the way, I should say that Zuckerberg is very keen about it, his own privacy, just not so much about yours. And I'm not sure if this is a question someone is asking with the phone, but I will continue. Okay, then surveillance capitalism is now a phrase to kind of describe this new economic system that is emerging out of this development we see with Facebook, Google, Amazon, Microsoft, but also insurance companies, governments, and many, many other companies are jumping on board. And the idea is they try to get access to as much data from you as they can, in any way they can, even if you agree or not, do not agree to it. And they try also to not just monitor your behavior, but also to modify your behavior. And all, you know, of course, just for profit. And unfortunately, this gets to the point where it's really disastrous for personal freedom, it's disastrous for the democracy, and it's disastrous for our social environment. Therefore, I think it's urgently needed that we stand up and do something about it. And of course, you could say, you know, pandemics, COVID, we need to relent some of our privacy so that we can keep this privacy on this pandemic under control. And this is what Google and Facebook want. And they also want to give you the feeling that there's nothing you can do about it. So just please keep on playing the game. There's nothing you can do about it. And trust us with your privacy. But of course, trusting Facebook and Google with privacy is like trusting Exxon and BP with environmental regulations. It's really not the way to go. Now, this brings me to the mathematical part of this talk. There's an urgent need for privacy-preserving machine learning and privacy-preserving AI, privacy-preserving data science. Because after all, I think it's all clear to us there's a lot of good that we can get from AI. There's a lot of benefits we can get from machine learning. Analyzing data can do a lot of good things for us, but we need to make sure that at the same time we preserve basic laws, basic rules of privacy. And this brings us to the emerging topic of privacy-preserving machine learning. There are several techniques that fall into this regime. One is homomorphic encryption, then federated learning or online on-device learning would be another one. Anonymization is a standard technique, differential privacy, and then finally synthetic data. These are kind of the key techniques one pursues in privacy-preserving machine learning, and in this talk I will only focus on the last three: anonymization, differential privacy, and synthetic data. It's not that the first two are not important, but for time reasons, I would not be able to cover all of them. And I really don't have anything interesting to say about homomorphic encryption anyway. Okay, so as you will see in this talk, one message to take away is the path to privacy is paved with MP hard problems. So this is really a mathematical challenge, or many mathematical challenges that we will need in our attempt to make privacy-preserving machine learning a reality. And let me start with the one very simple idea in privacy-preserving machine learning, namely anonymization. And the standard technique in anonymization is called k-anonymity. And the intuition there is that you have this database with many, many people. Think of the Census, for example. And k-anonymity is given when the information of one person in a data set cannot really be distinguished from the information of k-1 other persons. So in that sense, you're hiding in the crowd. You're hiding in the crowd of k individuals that are like you, or k-1 individuals that are like you. The precise definition is given here, but it's really just a mathematical description of what I just stated to you. So you try to have a database where all the, but no matter how you analyze this database, there are always k individuals that look similar. And to give you an example, let's look at the database on the left side here. You have people, and you have the properties of these people, and the database on the left side is not a k anonymous database. But we can turn it into one by suppressing certain properties or changing certain properties or making certain properties a little bit more general. And you'll see on the right side, the database satisfies the k = 2 anonymity. There are always, no matter what property you look at, there are always two rows that are identical. So in this case, we had to maybe suppress some first names. We may have to make the age a little bit more coarse grain. And so we end up with a database that satisfies the 2 anonymity property. This is a standard technique, has been used quite often. Unfortunately, it's also not that useful because it has its limitations. For example, if I bring in additional information, then it's fairly easy to break this k anonymity. You have maybe heard about this Netflix price.
Headers that we're going to apply.
Excuse me again? What's that question?
No, that was someone. I apologize. Someone was unmuted. They are muted now.
Okay, then let me nevertheless answer the question that I may have heard here anyway. So the Netflix prize is something you may have heard. You know, there was an idea to have another Netflix prize, but then they had to cancel this because it turned out the database they made public wasn't really anonymous. When you bring in additional information to a database like this, you often can break this anonymity. And in the Netflix prize, it was really combining the zip code with some vague geographical information and, some vague private information and social security numbers that were partially blocked. That was enough to break the database. So k-anonymity is very limited, yet it is still partly in use and also partly in use with other privacy preserving properties. The other standard tool right now is differential privacy. And differential privacy is a different take on privacy. It says, well, we cannot really guarantee that you do not use your data, but what we can guarantee to you is that nobody will be able to tell if we used your data in our data analysis or not. So if we have a database, we do some analysis, we get some conclusions based on this analysis. At the end, nobody will be able to tell for sure if your data were used in this analysis or not. So removing one entry in this data set, or exchanging one entry in this data set would not enable you to tell if we changed an entry or not. And the formal definition, going back to Dwork from 2006, I want to go through that because that's an important part of privacy preserving machine learning. So let me read through it and then explain the details. We have a randomized function m, and we say that it gives epsilon differential privacy if I have two databases, D1 and D2, that differ only in one entry. So think of the census, and you have the rows are the people, and you replace one row, or you remove one row. So you remove one person or replace one person by a different person. So this is what I mean with databases that differ by only one element. Or you have a set of images, and you with faces, and you either include an image or not. So that's the difference I mean here. And then you look at the range of M and look at subsets of that range of M, possible outcomes. Then the probability that you apply a data analysis on this one data set, and you end up in a set S, and you apply the data analysis to another set, D2, and you end up in a set S. These probabilities are very close. And so this is a way to measure differential privacy. And the lower the value of epsilon, the more indistinguishable they become. For example, think of epsilon being 0, then the probabilities on the left and the right are the same. That means it doesn't make it any difference at all if I remove one individual of the data set or not, I always get the same probabilities. This is, of course, asking a little bit much, but we aim for small values of epsilon, and this would guarantee differential privacy, or privacy in the sense of this particular notion. Now, how do you ensure differential privacy in practice? Well, the standard mechanism is to add noise to the data or to the data queries. So I could add noise right to the data. For example, if you think of the census and you have the age, I could add noise to the age entries. Or more typical is really I add noise to the data queries. So you're asking a question of the data set, for example, what's the mean age in this group? And then I would provide you the answer, but I will not provide you the exact answer. I would provide you the answer with some noise. So this is the typical way to implement differential privacy. And typically we use Laplacian noise, which means Laplacian noise sigma, where sigma scales like 1 over epsilon. And again, like before, the lower the value of epsilon, the more noisy the data and the more privacy you have. So you're hiding instead of in the crowd with k-anonymity, here you hide in a noise. And on the other hand, in practice, the challenge is now, how should I choose this epsilon? We call it the privacy budget. What's a good choice? And I just tell you, in practice, a typical choice is something like epsilon is less than 4, even though you see analysis where epsilon is sometimes in the order of 10 or 100. And let's go back to the definition. If epsilon is 100, then really this becomes very meaningless. So this is really a challenge here in differential privacy, this trade-off between privacy and utility of the data, right? If I add a lot of noise to the data, then the data become very private, but also potentially very useless. And differential privacy is a tool that is really used in practice, like k-anonymity. For example, that will be used in the release of the Census 2020 data. And when I say release of the Census data, what they will really release is answers to data queries, which are then protected by differential privacy. Coming to synthetic data. So we talked about differential privacy, we talked about k-anonymity. What is synthetic data? Well, synthetic data is the idea that I have a data set which I would like to release, but I cannot because of privacy protection reasons. So instead, I release a synthetic data set. This is a data set that's kind of like the real data set, but not quite. It's a made-up data set that preserves key properties of the real data. I have to, of course, define what they mean here. And I do it in a way without exposing private information. So in a way, it's the real thing, but not quite. And you see we have an intrinsic conflict here between privacy and utility for synthetic data. Because on the one hand, synthetic data should be different from the original data, but on the other hand, they have to be similar, right? Otherwise, it's not really doing the thing that I want. And we can look at two extreme cases. We can choose the synthetic data to be exactly equal to the original data, then have perfect utility. They are as good as the original data, but of course, I have zero privacy. The other extreme is I just release random data. Then I have perfect privacy, but they're completely useless. And I have to find, of course, now a way to do something in between and do it in a mathematically provable way. And there's a big movement in trying to combine synthetic data with differential privacy to overcome some of the limitations of differential privacy. I told you before, differential privacy is usually tied to not releasing the entire data set, but just to releasing answers to the data set that I now protect with some privacy. So you're asking questions from my data set and I release answers to you, but I'm not handing the data set to you. And this is not really very desirable. So synthetic data combined with differential privacy should overcome that limitation so they can actually hand over the data set to you and you can do with it what you want. But it's not exactly the real thing. It's kind of a protected data set. So to understand the difference between all these different notions, let me give you an example. So let's look at this image on this panel on the left side. It contains a lot of images of faces. And k-anonymity or anonymization would work like what I have drawn in the writer-up image here, where you have all the eyes blocked out by the individuals. This would kind of be a symbolic representation of what anonymity tries to do. It tries to hide some information that makes you not recognizable. Differential privacy is a different way of doing that. It's depicted symbolically in the panel on the right below, where we add noise to the data. So we blur information in a certain way. In both cases, there's a clear loss of information. It's a different loss of information, but it's a loss of information. And synthetic data instead tries to do what I have depicted here. Again, on the left side, you have the true faces. On the right side, I try to create artificial faces. So none of the faces on the right side are really faces from people that exist. Well, they look real. That's the idea, right? But they're not real. They're constructed from the faces on the left side. Now, how do I know that this is, just saying they look real doesn't really mean much here, right? Because the faces on the left side, let's say they are, I don't know, 100 people and 20 of them have glasses, 20 of them have a beard, 10 people are bald, 3 people are African-American, 7 people are white, and so on and so on and so on. Is this preserved in these artificial faces on the right side? And there could be other, more nuanced characteristics that we need to preserve in the synthetic data set. So just creating faces that look real, that you often see, when people demonstrate the power of neural networks. That's not really useful for us, right? We need to be much more specific here. We need to make sure that we preserve important properties, and we need to capture this in a mathematical, rigorous way. And at the same time, we need to make sure that we're not reproducing the real faces. Otherwise, we are, violating privacy. So this is the framework in which we have to work. So we need to make sure that the synthetic data set captures the nuances of the real data set, and at the same time, not too much so that privacy is preserved. Now, one of the directions that we are, or the topics that we are working on is not really the faces, but it really comes from health medicine, because this is really where there's this huge urgency of privacy. It's much more pronounced than in many other areas. And the area that we are working on is the intensive care unit, partly related to COVID, but also partly because it's an important domain in its own right. And data analysis is really important there, because there are many applications, many situations in intensive care unit. If you had better data analysis, better prognostics, then you could do a much better job. The problem is the ICU at the hospital usually does not generate enough data to do a really thorough data analysis by itself. So you would have to share data across hospitals, across the United States for many, many, many ICUs. And this is where the problem is. There are a lot of difficulties of sharing data, and rightly so. I'm not saying we should remove these difficulties. No, they're there for a reason. At the same time, we would like to share data to do a better data analysis. And this is a real bottleneck now. And in particular in the ICU, treatment is very expensive, life-side stakes. So this is really an area where we would really make progress with synthetic data, so that we can release synthetic data across ICUs, across the country, analyze them, and then draw conclusions that are useful for real data and then have real impact on ICU treatment. So this is a topic that we're working on. The challenge there, one challenge there, is the data are heterogeneous, they are multimodal. That means you have all kinds of different data. You have images, you have X-rays, you have microscope, well, I can't say the word right now, so let's say time series analysis. You have tabular data, you have handwritten notes. So you have all these different kinds of data that belong to one patient, and you want to merge all this data in a meaningful way and create a synthetic data out of this multimodal data. And this is the task that you try to do. Well, it turns out it's really, really hard, and we need to start with something much more modest. So this is what we want to do. And now I tell you what we're doing. We start with a simple benchmark model. As a mathematician, we first start with something that we think we can understand really well. Let's start with a very simple model, build it up from there, and then become more and more ambitious. Our data model is the Boolean cube. So data sets for us are just matrices with n rows and p columns, and the entries are zeros and ones. This is our data model for now. And you think this is overly simplistic, but actually it's not such a bad data model. For example, electronic health records are often modeled via the Boolean cube. Think of the rows of the data set of this matrix X. The rows are the patients, and the columns are the different properties that we want to know about the patient. For example, the first column could represent if a patient smokes or not. 0 is not smoking, 1 is smoking. And the second column could be, is the patient diabetic or not? The third column could be the age of the patient. Well, for the age, we have to encode it on a Boolean cube by saying, for example, doing it in age groups, maybe from 0 to 5, 5 to 10, 10 to 15, 15 to 20. Then we can do some binary encoding and map it onto the Boolean cube. Gender, occupation, we have to do some one hot, or rather all hot encoding. This is what I would do, and you would map it onto the Boolean cube in that way. So you can represent patients on the Boolean cube, at least approximately accurately. Or the census data, for example, it's very common to represent the census data on the Boolean cube, again, for the procedures I described below. So the Boolean cube is a very useful model to get us started. And it's a simple model, right? So how hard can it be? Well, before we talk about how hard it can be, let's talk about how we measure accuracy, how we measure usefulness of our data. And one way to measure usefulness, accuracy of data on the Boolean cube is by looking at marginals. So we compare the marginals of the original data with the marginals of the synthetic data. And the marginals here, for example, one-dimensional marginals would simply mean how many patients are smoking, how many patients have diabetes. These are one-dimensional marginals. How many patients are between 5 and 10 years old. Two-dimensional marginals would be how many patients are smoking and have diabetes. Three-dimensional marginals would be how many patients are smoking, have diabetes, and between 35 and 40 years old, and so on and so on and so on. And you would like to preserve the marginals of your data. At least you would like to preserve the marginals of your low dimensional, excuse me, you would like to preserve the low dimensional marginals of your data. You do not need to preserve all high dimensional marginals of your data, because that could mean I'm looking for a patient who is smoking, has diabetes, is between 35 and 40 years old, is male, lives in San Francisco, drives a Volvo, and so on and so on, and there's only one person left, right? So if you try to preserve high dimensional marginals, you enter the area where you cannot protect privacy anymore. But low dimensional marginals is something we definitely would like to preserve. You already see a kind of uncertainty principle hiding here between preserving accuracy and revealing privacy, which could be described by marginals. Okay, so we measure accuracy. In this case, let's say we are preserving accuracy of marginals. And by the way, since we're on a Boolean cube, for those of you who are familiar with Fourier analysis on a Boolean cube, so Chris, that's for you. We could encode the marginals by the Fourier coefficients of this of the marginals. So we go in the Fourier domain on the Boolean cube, look at the Fourier coefficients, and they would encode the marginals. So there's a nice connection between the data analysis and Fourier analysis on the Boolean cube. Okay, so our goal now, mathematical goal, is we have given data on the Boolean cube, and we would like to create synthetic data. That means we would like, you give me the original data set, I put out a synthetic data set. It doesn't have to be the same number of patients. Let's always think of the health record as a kind of toy example. So you give me a data set with original patients. I create a synthetic data set which may or may not have the same number of patients. That really doesn't matter. But I want them to be private. That means in this case, let's say I want differential privacy. So if I remove the data, one patient in a data set you gave me, and I create a synthetic data set, I should not be able to tell if that original person was part of the data set or not when I show you my synthetic data set. So privacy. Accuracy. I would like to, that the low dimensional marginals are close to the low dimensional marginals of the original data set. And efficiency. I would like to create this data set in a reasonable amount of time. I don't want to wait 1,000 years. So the runtime should be polynomial. We should not be, doable in theory, but infeasible in practice. So these are the goals, right? Boolean cube, very simple. How hard can it be? Well, it turns out it's NP hard. So even this very simple problem, seemingly simple, it's not simple as we see, with the Boolean cube is NP hard. There's a deep result by Ullman and Vadan from 2011 that says, well, you can't have all those four. If you want to have efficiency, then you have to throw out one of these three properties, or you throw out efficiency. Well, we cannot throw out efficiency because we want to be able to compute the data. We don't want to throw out synthetic data. That's the whole point. Well, privacy needs to be protected, so let's see what we can do about the accuracy. Now you might say, can't I just create synthetic data by simply adding noise to the Boolean cube data that you give me? That's, you ensure privacy. This would be the most simple way to do it, right? Computational efficiency is there. It's synthetic, it's private, but it's not accurate. If you add noise simply to the raw data and release those, the marginals would be terribly off. You would not preserve the marginals. The accuracy would be terrible. Or you have to add so little noise that the accuracy is okay, but then the privacy is terrible. So just adding noise to the data doesn't really solve the problem here. So but it's NP hard, this problem. What do we do? And we will present to you two ways how we can resolve the NP hardness here. One is this condition on all marginals have to be preserved accurately. We will relax it to almost all marginals have to be preserved accurately. Okay, so we relax all to almost all. This is one relaxation. The other relaxation, so we will see one result for that, and the other approach we will take independently is, but this result, this no-go result by Ullman, Vadan, this NP-hard result is really a worst-case result. It says that, there is a data set for which this is NP-hard, but this may not be true for typical data, right? So maybe this is just a worst case result, but for typical data, maybe it's not NP hard. And we will develop a statistical framework where we'll be able to show, yes, actually you can have all 4 properties if you go from worst case to typical case. And these are the 2 mathematical results I will present to you. I will present another result at the end, but these are the first 2 results. So first we will talk about moving from all marginals to almost all marginals. And we will start again by looking first at the k-anonymity. I described what k-anonymity is, and let's start first with k-anonymity. You know, maybe differential privacy is too hard. Let's try k-anonymity first. You know, you give this data set on a Boolean cube, and I want to construct a k-anonymous data set that is accurate, synthetic, and, well, k-anonymous. And I want to do it in a computationally efficient way. So I'm using a weaker notion of privacy. That should be possible, right? How hard is it? This k-anonymous I showed you, we just suppress some entries. This cannot be that hard. Well, it turns out, again, NP hard. So even this simple problem is already NP hard. And unfortunately, on our path to develop privacy-preserving machine learning tools, we always encounter these NP hard problems. This is not an excuse for Google and Facebook. It just means we need to work a little bit harder to make this possible. Okay, we will stick with k-anonymity nevertheless, even though it's NP hard, and go from there. The classical way to achieve k-anonymity, but without any guarantee of accuracy. You know, k-anonymity has been around for 20 years, but nobody has given any bound on achievable accuracy. They just prove that the data set I created is k-anonymous, but it's not, there's no proof about accuracy at all. So this is an open problem for 20 years now. And the classical way to achieve k-anonymity, the most useful way actually, is called microaggregation in the literature. What you do is you have given this data set X. It doesn't have to be in a Boolean cube, that works in general. You first cluster this data set X into clusters of size at least K, and then in each cluster, I choose a representative. Okay, so I have my data set X. I cluster this data set so that each cluster has at least K points. Of course, I'm grouping similar things together in that way. And then I replace each cluster by one representative from that cluster. It could be the centroid or some other way how you choose some member from that cluster. This is microaggregation. Okay, clustering and replacing the cluster by some meaningful representation of the cluster. Now, again, I told you before, trying to do microaggregation and getting you get k-anonymity, but getting accuracy is an NP hard problem if you want to do it in a computational, well, if you want to do it for all marginals. Okay, so what do we do about that? Well, as a mathematician, well, let me first tell you a few challenges of k-anonymity. Well, real-world data sets are high-dimensional and very sparse, so already have a problem there why this is computationally so expensive. You know, if you do clustering in high dimensions, finding k-1 neighbors to a data point is computationally very expensive. So this is one problem. Then how do you control accuracy? This is another problem. You could say, well, I project onto lower dimensions. Yes, you can do that, but you need to make sure that you do not lose important information. How do you control that? And so a lot of issues that come up with this microaggregation approach. Now, we tried to solve this, and we solved it by doing something completely different first. So instead of looking at k-anonymity, we looked at a different problem that has nothing to do with it at all at first. We looked at a problem from theoretical probability. And the problem we looked at can be phrased what I have written here. How much information is lost when we take conditional expectation? This is a very basic question from probability, right? Conditional expectation is something that we do all the time in probability. And I ask you now this very basic information, basic question. How much information do I lose when I take conditional expectation? You know, I must be able to answer that, right? That's such a basic question. Now let's look at an example. I have a random variable x and a sigma algebra f, and I consider the typical conditional expectation y in expectation x based on the sigma algebra. This is the basic starting point of conditional expectation. Now, the law of total expectation tells us that y gives us an unbiased estimate of the mean of x, right? The expectation of x is the same as the expectation of y. So far, so good. Nothing lost there. But let's move to variance. The law of total variance that I've written down here tells us that taking conditional expectation underestimates variance, right? Because the expression on the left side, if you look at the difference between variance of x and the variance of y, on the right side you have a positive term. So the variance of x is provably larger than the variance of y. And unless you have a very, very special case. But in general, the variance of x is larger than the variance of y. So you always underestimate the variance. And that's kind of annoying. Now, you can ask, how much do I lose? How much variance is lost here? This is a very, very basic question in probability, right? Well, let's see. Let's start with a very simple example. One-dimensional example. We take a bounded random variable. So let's say x is bounded between -1 and 1. We decompose this into an interval, into k subintervals, each of length 2 over k. And the sigma algebra is defined in that way based on this partition, right? The sigma algebra is always related to some partition of the space. So we partition interval, uniform subintervals, this generates my sigma algebra. Then in this way, if I can bound the loss in variance by 4 over k squared. It's a very simple calculation. You see that the variance loss here is bounded by 4 over k squared. This is not bad. That's a good result. It scales very, very well. Unfortunately, if you go to high dimensions, this doesn't work at all, because that would mean, well, it would work, but it would mean that the sigma algebra, because you're in high dimensions, would have to have a lot of partitions. So you would have a large number of subintervals, and because we hit here the curse of dimensionality here, right? So we can generalize this into high dimensions in which way? Well, the law of variance becomes the law of of covariance, right? Variance is replaced by covariance. So x is now a random vector, y is the conditional expectation of x based on the sigma algebra, and we look at the covariance matrix associated to x and associated to y. Again, a very basic thing in theoretical probability. And if you do the calculation, I see that the covariance matrix of x dominates the covariance matrix related to y in the sense of order of semi-definite matrices. So there's always a loss of covariance. Like we had a loss of variance. There's a loss of covariance in high dimensions. And now we can ask, well, how much information do we lose here? How big is the covariance loss? And what, if I want to control this covariance loss, how can I choose the sigma algebra f as good as possible if I want to have it small? I don't want to have a very large sigma algebra. I want to have a small sigma algebra. So I give you a certain cardinality of the sigma algebra. How can you choose construct the best possible sigma algebra to control the covariance loss? A very basic mathematical, very fundamental question, right? And as I said, we face the curse of dimensionality here. If you do what we did in one dimension, you just split up the high dimensional space into uniform subintervals. You would need exponentially many in k subintervals, and this is really not a good way to go. So k would have to be exponentially large in p, in the dimension of the random vector, and this is not what we want. This would be immediately lead to computationally infeasible problems. So how can we control the covariance loss? Well, here's a theorem that we proved that tells you this is as good as it gets. We can control the covariance loss by choosing a sigma algebra that we can construct this explicitly. So you give us the cardinality k, and we can construct the best possible sigma algebra explicitly. So it's not a theoretical thing. I can do it really on a computer. And then I can give you a bound on the covariance loss. As you see it here, the sigma x minus sigma y bounded in the Frobenius norm is bounded on the right side by 1 over the square root of 1 over log k, and in the numerator we have log k. So this bound is optimal. except for the log-log k-factor. And log-log is really, really small. So this is, we can prove that this is the best possible you can do. And this is an answer to the completely theoretical question. And by the way, I can extend it to higher dimensions. I can go to higher moments. You see this by the equation you see in the bottom, where we can extend this to higher moments in a kind of almost magical way, because if you think back what I said about Fourier analysis and marginals on the Boolean cube, it seems strange that if I give you Fourier coefficients, you know, the first and second coefficients, that you can say something about the third coefficient, right? Because they are orthogonal. The frequencies are orthogonal, so you shouldn't be able to say something about them. But in this way, actually, you can say something about higher moments as well. Okay, I told you about covariance loss, something completely theoretical about, you know, something that has nothing to do with privacy. Now we will make the connection. Now we will connect covariance loss to differential privacy and k-anonymity. So we give now two data. We're back to the data set of patients. We have the health record. I have my data set x1, xn, which live in RP. It doesn't really have to be the Boolean cube here, but it's convenient to think about it in that way. I generate a random variable capital Xi, which has as entry little xi. So this is my random variable. And now I'm asking my covariance loss question for this random variable. And so the goal here is, of course, I would like to bring in this sigma algebra partitioning that controls the covariance loss. And what we do here is we connect the covariance loss to a bound on the marginals of these two data sets that they have, the original data set X and the new data set Y that comes out of this partitioning of the sigma algebra. And this is the microaggregation step I described before to you. So this is what we really do here. We combine a result from theoretical probability to something very practical, namely microaggregation. And obviously this is n over k anonymous if you do it that way, that I microaggregate the data by creating first this sigma algebra. This I can do constructively based on a theorem before. Then, you know, for each partition, I do this averaging. This is clustering, and then finding a representative of this cluster. So this is the step we do here. First clustering, which is the partitioning, finding a representative of the cluster by averaging. This is microaggregation. And based on the theorem I told you before, I can show now that if I have my data X, the original data, and my data Y, the new data, the synthetic data, then the moments of this data are bound, the difference of the moments of this data, which are the marginals really, is bounded by this expression on the right-hand side. So I have a bound on the accuracy of my synthetic data. D equals 1 means it's just one-dimensional marginals, you know, these are the means of the data. D equals 2 means we are talking about two-dimensional marginals or covariances of the data. D equals 3 and so on for you go to higher and higher marginals. And what we have here is really a bound on the accuracy of the data. Now, this is k-anonymity. It's not differential privacy. It's only k-anonymity. But we can add differential privacy by adding noise to the data. Now, I just want to leave out a few details here, but just point out one thing here. You might say, well, how hard can this be to add differential privacy here? You know, this whole microaggregation thing seems very basic. You cluster data and, you know, so what? Well, let me give you a simple example here. This is a data set, and let's say we try to achieve k equals 4 anonymity here. And we want to do it in a differential private way. Well, if I take this data set and I group it into groups with 4 members in each group, then this is what we get. And the red dot is the representative I choose based on the centroid of this data set. Okay, so this is basic clustering, right? So what's the big deal here? Well, differential privacy means if I remove one data point, the result shouldn't change much. So let's say we remove the data point that I have marked here on the left low and the lower left with the blue arrow. Let's say I remove this data point and I repeat my exercise. What I get is this. Not much has changed, right? That's what I want with differential privacy. So everything seems to be fine. But what if I remove the point up here on the right? So my data set is before, but now I remove this point up on the right and I repeat my exercise. All of a sudden, it changes to this. You see this change of the red dot. On the red dot that represents this one kind of larger group here. If you remove this one guy here, then you see how this red dot moves. So the big move of this red dot tells me here, oh, this guy was not present, right? You see this change, this big change. You could say, well, this was a very mean data set you chose here. You know, what if it's more nice like this one here? Well, okay, let's try. This is one obvious way to cluster this. We have the representative. Let's say we remove this one guy here. Well, not a big deal here, right? What if you remove this guy here, and you see how things change again? You know, let me come back to this, and you see how this red dot changes again a lot. Well, you might say this is kind of silly. Who cares about this? Well, we care in connection with the census. There's a lot of bad news regarding the census release with differential privacy. People, homes vanished due to the 2020 use of census use of differential privacy. You know, minorities really have problems with the release of the census that is differential private, because there are a lot of problems with minorities being undercounted. There's a lot of, unfortunately, undecided bias that minorities get undercounted. And Native Americans have a big problem with that. For good reason, because if you think you have 100 people living in your community and the census tells it's only 20 people, the money that you get allocated is, you know, vastly different. So what I just mentioned to you, this moving these red dots around, this is really an issue with the census. So this is really a real world problem. I just broke it down to a simple mathematical problem, but this is really a major problem now. And coming back to our first algorithm, well, we have an algorithm that really does this microaggregation in a projected space. So what we do in this algorithm is we do spectral projection, then we do this nearest neighbor partitioning that I described to you. We carefully choose how we add noise to the data. We can bound all these steps with this covariance loss I described to you. I'm leaving out steps here, but the covariance loss theorem, the theorem I mentioned to you, is in the background all the time. It allows us to control the error in each step. And at the end, what we get after the steps at the list here is differentially private data that are accurate, that are computed in polynomial time, and that, we can have explicit bounds on the accuracy. And here's the theorem that tells you that. I'm not taking you through this. The proof is a long proof. You have to be really careful with all the keeping track of your privacy. But this is the result. So this is the first result on microaggregation that shows, well, this MP hardness can be sidestepped if you replace the conditional all marginals by almost all marginals. This is the first result I want to present to you. The second result is, well, based on this result that I presented to you suffers from low accuracy, right? The bound you get is square root of 1 over log k. And I told you this is almost the best possible. So this procedure that we described to you is only good if k is really large. So if you have 1,000 people in a group, it's okay. But if you have only 10 people in a group, it's not good. So the question is, well, since we showed that microaggregation clearly has its limits, is a different way to go about it. And this brings me to the statistical framework. This is the other approach. So I told you that the Ullmann result tells us you cannot have synthetic data that's private accurate, and you can do it in a computational feasible way. This is MP hard. But this is a worst case result. What if I can develop a statistical framework that tells you, well, you know, we don't see this worst case with kind of data very often, or maybe not at all. What can we say about typical data? And this is what we try to do here. So we assume that our true data, again, census, for example, is a random sample from some probability space. And that probability space comes with some probability distribution mu that specifies the population model of the true data. But we do not know mu, right? We don't have access to it. So we cannot just resample from this space to create synthetic data in that way. If we could, we would do it, but we don't know that probability distribution. But let's assume we can sample from omega, you know, from the data space. according to some other distribution. And just to give an example for the Boolean cube, again, think of the health records. These are data on a Boolean cube. There's some underlying distribution of the patients. We don't know that distribution, but we can sample randomly from the Boolean cube in any way we want, right? We can do that. So I do not have to know the true distribution to sample from the Boolean cube. So I can just do it in that way. But does it help me in any way? Well, this is what I try to convince you. Yes, this is actually enough already to make progress on constructing synthetic data. Again, how do we measure accuracy? Well, in this case, it can be marginals, but let's be a little bit more general. Let's say we use linear statistics. It's more general than marginals. So any, as I describe here, we use linear statistics to describe what we want to learn about the data set. And we want to preserve linear statistics up to some delta. And here you see this is not almost all, this is all. We want to preserve the maximum error here. So this is for all linear statistics that you choose to preserve. We want to achieve this delta accuracy. Now the point is the cardinality of omega is often too large to do computations. We want to have something that's computationally feasible. The Boolean cube itself is too large. It's usually too expensive to do Boolean computations on Boolean cube if P is large, like it would be for the census. However, the linear statistics you try to preserve is usually a much smaller set. So, for example, if you try to preserve the lower dimensional marginals on the Boolean cube, then this is something that's polynomial in P, while the size of the cube, the cardinality of the Boolean cube is exponential in P. So we would like to do the computations not on the Boolean cube. So the question is, can we maybe downsample the Boolean cube randomly and just work with a subset of it? So on the one hand, we don't really know the true population density, and I want to subsample on the Boolean cube. So I do two things that really I shouldn't do in a way. Can I do that? I subsample and I choose a different wrong density from which I sample, then I construct synthetic data. All this seems very weird and doesn't really seem possible to do. Well, it's not possible in general, but it's possible if I have some correlation between the true population density of the data and the sampling distribution that I use. And I measure this correlation. I need to make this mathematical rigorous. And I can measure this correlation by using something that we call the Rainey condition number. The Rainey condition number describes the similarity of two distributions. That's in the way how we define it. Of course, it's based on a Rainey divergence. And the Rainey condition number is 1 if two distributions are the same, and it's larger than 1 if they're not the same. So it's like the condition number of a matrix in a sense. And based on this Rainey condition number, we can derive an algorithm that produces synthetic data. I just described the algorithm to you here. You give me the linear statistics you'd like to preserve. Let's say all marginals up to degree 3. Then I add noise to this linear statistics in a certain way that preserves differential privacy. Now I construct a density based on the linear statistics that I try to preserve. So I know the linear statistics of the true data. I try to find synthetic data that preserve these linear statistics up to some error delta. And I try to do it in this reduced space omega star, where I simply sample from the Boolean cube randomly data, and I work on this reduced space. So I'm on a subset on the Boolean cube, a very small subset, and I solve this linear program. This is a linear program you see here. I solve this linear program on this reduced space. I solve it, I do a bootstrapping, and I have my synthetic data. Okay, so I add noise to the linear statistics. I set up my reduced space of the Boolean cube. I reweight the density. I bootstrap. I'm done. Can this work? And the theorem tells you, yes, this works. This simple procedure works. I can preserve privacy in this way if these parameters are satisfied. I can preserve accuracy in this way. And you see what you see here is in the accuracy, the Rainey condition number comes in here. You need to make sure that the data, the parameters of the data set satisfy these conditions where the Rainey condition number critically comes into play here. I'm not going into detail here, just telling you in this way you can construct synthetic data where you preserve statistics exactly, but you do it only for typical data. It doesn't work for all data, but for typical data sets. So for random draws of the data set. Now, since I'm running out of time, I want just to point out a few more things. So we have an algorithm that can construct synthetic data on a Boolean cube via this microaggregation approach that works for. There's no condition on the data set because it really doesn't have to be the Boolean cube as long as it's some convex set. But it only works for almost all data, and the accuracy is not that great. Here we have an algorithm that conserves all linear statistics, but it works for typical data, not for all data. And also we add noise to the data like in the other case as well. So the big question now is, differential privacy always seems to require adding noise. Can we do without adding noise? Has anyone ever constructed differential private data without adding noise? Is this possible? So far, not. Nobody has found a way to create differential private data without adding noise. And we didn't like this, so we came up with a way to actually do it. It's a scheme that we call private sampling. Private sampling allows you to achieve differential privacy without having to add noise. So this is the first way to achieve differential privacy without having to add noise. We can do it, we can prove it so far for the Boolean cube. There's a lot of Fourier analysis on the Boolean cube coming in, hypercontractivity, duality, empirical processes, a lot of deep mathematical tools that we use in constructing this private sampling scheme. And again, this is 30 pages of proof, something I cannot do here. Let me just tell you one simple lemma that is at the core of this differential privacy. This simple lemma says, you have a finite set omega, and this private sampling lemma says, you have a mapping F that takes this data set X as input and returns some probability mass function f of X on omega. Okay, so this is very basic. You have a data set X, you have a mapping that takes X as input and gives you a probability mass function. Now, assume I have two, now I'm bringing in differential privacy. I have two data sets, X1 and X2, that differ only by 1 point. If I can make sure that this mapping is bounded in the way I have written here, that the ratio of this f of X1 and f of X2 is bounded in infinity norm by this expression on the right-hand side, if I can prove that, then I can assure you with an algorithm that you can now sample randomly from omega, and you will get a differentially private result. So this lemma is really at the core of this private sampling strategy that we have developed. Make it into an algorithm that constructs synthetic data requires 30 pages of very tedious mathematics, but it's possible, it's doable. And so let me just bring you to what we are trying to do right now. We try to see if we can really improve on the census data that will be released soon by using this private sampling mechanism, because this has real-world impact for people. So the question that we try to study now is, can we use this private sampling strategy to achieve better results for a differentially private census? And the last thing, we're still working, so I talked a lot about the Boolean cube. What we really want to do is work on this multimodal synthetic data on the ICU. We are still working on this. This has a long way to go, but I showed you that even the simplest questions on synthetic data and privacy are already NP hard, so it's no wonder that this is a quite hard problem to work on. If you want to read up on anything that I told you here, you find these papers on the archive on my homepage. They contain all the mathematical details. And otherwise, thank you very much for listening. I wish you a very good Dia de los Muertos.